Welcome to the third lecture of the course turbulence. So, before I proceed, I would like to give you the brief recap of the stuff we have covered in the last class. So, mainly in the last class we have talked about origin of turbulence, then we have started talking about the the mathematical procedure to predict the critical Reynolds number. Okay. So, while doing so, we have considered the governing equations, and that were one continuity equation and another one momentum equations. So, momentum equations for in Cartesian coordinate system, we had 3 equations for x momentum, y momentum, z momentum. So, then we said that these equations will satisfy both the basic flow as well as the disturbance, okay, basic flow plus disturbance. So, based on this we could figure out the disturbance equation, and after linearizing and considering the parallel flow approximations, we could arrive to this set of equations. This is the disturbance equation, continuity disturbance equation, and this is the disturbance equation for x momentum equation, and y momentum disturbance equation, and z momentum disturbance equation. And these equations I think we named as 2, 5, 6 and 7. Okay. So, let us proceed from this set of equations today. Okay. And these equations, as I have mentioned, we have achieved this set of equations based on the parallel flow approximation, okay, as well as linearization. So, based on this parallel flow approximation and linearization, we could arrive to this set of equations. Okay. Then we consider the travelling disturbance as the travelling waveform or the normal mode. Okay. Normal mode, because we consider that disturbance will be of the travelling waveform, and each and every or individual frequency will govern the instability, okay, rather any interaction between them. Okay. So, that is what the the normal mode. Okay. So, let me write once again. So, in the last class, as you can remember, that we wrote that u prime, then v prime, w prime and p prime equals to your u hat, okay, which is a function of y only. Okay. These are Fourier amplitude, keep it in mind. So, at particular y location, and this is v y, then w hat of y, then p hat of y exponential I alpha x cos phi x should be there, x cos phi plus z sin phi minus c t. Okay. C is the phase velocity. Okay. So, this is what we consider. Okay. Now, why we consider like that? We have already told in the last class that this is a travelling waveform, and why it is travelling waveform, because it is written in as a function of x minus c t, okay, or alpha x minus omega t, okay, which is a travelling waveform. Now, this is you can also consider as a particular component of particular Fourier mode. Why? Because for example, just for example, okay, let us consider a function f of t. If f of t is a function of t alone, then we can write this as a naught plus a 1 cosine 1 omega naught t plus b 1 cosine 1 omega naught t plus we can write a 2 cosine, this should be sine, okay, cosine 2 omega naught t plus, okay, plus b 2 sine 2 omega naught t and so on. Okay. So, this essentially can be written as a naught plus summation of 1 to infinity n cosine n omega naught t plus B n sin n omega naught t. Okay. So, this is what we can write, okay, where A naught is equal to 1 by t t naught to t naught plus capital T is the period, okay, of the disturbance, okay, f of t dt, okay, and A n is equal to 2 by t naught plus capital T f of t cosine n omega naught t dt, and B n is equal to 2 by capital T naught to t naught plus capital T f of t sin n omega naught t dt. Okay. So, these are the coefficients or Fourier coefficients, and you see here. So, any periodic disturbance, for example, any periodic disturbance of this sort, okay, can be represented by some Fourier modes like this. Okay. Suppose this particular sinusoid is related with omega 2 or 2 omega naught, okay, means second harmonic, let us say. If it is related with only second harmonic, then only your A2, okay, A2 and B2 will be sort of non-zero, all other coefficients will be 0. If it composed with several such frequencies, let us say 2 omega naught, 5 omega naught, 7 omega naught and so on, then the corresponding coefficients will also be non-zero, okay, and the particular value of this coefficient will tell us the contribution. The higher the value, higher the contribution of that particular frequency in that particular signal. Okay. That is what the this particular analysis says us. Now, our any disturbance component, let us say, it can compose of some sort of wave like this or some sinusoid like this. Okay. So, if we consider our general sinusoid, here it is not only a function of time, but we have also considered a function of x. So, here instead of function of t, if it is a function of x and t, then we can write this in this fashion, because why? Because this particular Fourier series. So, this particular series, this one can also be, so this f of t is equal to this. So, that also we can write this sorry. So, this also can be written in terms of complex representation. We can write as minus infinity to infinity capital F n exponential I n omega naught t. Okay. We can also we can also write this in this fashion, since we know e to the power I t is equal to sin t plus cosine t plus I sin t. Okay. Using this, okay, you will be able to show that basically this and this expression and this expression are basically same. So, we can write this particular series in terms of complex notation like this. Okay. Now, instead of this function as just as a function of t, it can be a function of x and t both. So, in that particular case, we can write this in both, provided that it is periodic in x and t both, then we can write this x alpha x minus omega t. Okay. So, this is what has been the form here, please do understand, and it is also known as normal mode, because the instability of a particular flow is governed by individual frequency which do not interact with other frequencies. Okay. So, that is why the most general form of the disturbance has been considered to be this particular travelling form. Okay. So, here you just you see, if f of t, instead of f of t, if it is just f of x, then here instead of omega naught k naught will be what spatial frequency or wave number in unit length, how many waves are there. So, that is the frequency, right. Similarly, omega naught in one period of time, I mean or in unit time, how many omega are there, or how many waves are there. Okay. So, this is something circular frequency. What is that basically? Omega naught is equal to 2 pi by capital T. Okay. Capital T is the period. If it is k naught or wave number, k naught you can write 2 pi by lambda. Lambda is the wavelength. Okay. Keep it in mind. So, anyway, so this is the disturbance form we have considered. Okay. After considering this particular disturbance form, let us see how we can simplify the equations 2, 5, 6 and 7. So, that is what we would like to see here. Okay. Equation 2, you see equation 2. So, equation 2, if you see here, it is del u prime del x, del v prime del y, del w prime del z. So, u prime means what? U prime in terms of normal mode can be written as u hat into exponential I alpha into x cos phi plus z sin phi. Why this particular x and x cos phi and z sin phi is coming? Let me just explain you why. Let us say this is your flat surface and this is the flow direction, okay, and let us say this is your z direction, this is z and this is your x direction, this is your x direction. So, we could have considered the wave is propagating in this direction. Instead of that, we are considering that most general form of the wave, we are considering in this particular plane wave is propagating at some angle to the this is the. So, this is what is your phi here. Okay. So, we are considering wave is not propagating along this line, rather wave is propagating at a particular angle with the x axis. Okay. So, that is the most general form of the disturbance, that is why this particular part has come. So, if you see I alpha, if you consider alpha x alpha cos phi plus your z alpha sin phi minus alpha into c your nothing but omega t. Okay. Omega is your alpha into c is equal to omega, alpha into c is equal to your omega, it is circular frequency. Okay. C is the space speed, alpha is the wave number. Okay. So, you see this is, if alpha is in this direction, its component in the x direction, that means that is k x or alpha x, and this one alpha z. So, this is x component of the wave number, this is z component of the wave number. Okay. So, instead of that we could have written as x k x plus z k z, okay, minus omega t, okay, instead of this cos phi and sin phi. Okay. So, this is nothing but to consider the most general form of the disturbance which is propagating at some particular angle with the x axis. Okay. That is why this cos phi and sin phi has been considered. Anyway, so here our u prime is basically u hat into exponential I alpha x cos phi plus z sin phi minus c t, right. Similarly, your v prime is equal to v hat exponential I alpha x cosine phi plus z sin phi minus c t, okay, and so on for w and w prime and p prime. Okay. So, now if you consider this particular expression and plug this expression in the equation 2, then what do we get? We will get so we have, what do we have to do? Del u prime del x, that means you are going to get I alpha u hat I alpha del x, right. So, with respect to x, that means cosine phi, I alpha cosine phi into that exponential, which will be common to all this term. Okay. So, now, so from equation 2 you write, from equation 2, okay, we get this, after using this expression in equation 2 we get, okay, this I alpha u hat cosine phi, then your v. Okay. So, del v prime del y, right. So, that means it is going to be v hat prime. Here this any prime in this particular symbol hat is considered to be derivative with respect to y, keep it in mind. So, here that del v, if you take the derivative with respect to y of this equation in both the side, then you are going to get, okay, this v hat prime into this exponential, which is common in all the term, that is what I have not written, okay, plus then you can write I alpha sin phi equals to 0. Okay. So, this is what you will get it. Okay. So, note that. So, using this particular expression in equation 2, this is what the equation we got, and let us say this equation is our equation number 8. Okay. Now, similarly we use this expression in equation 5, 6 and 7, and we can get out the corresponding equations. Okay. So, if we write those equations now from equation, so let us write from equation 2, 5, 6 and 7. Okay. We get these, then from equation x momentum equation, what we can write? So, that is remember that first term in the equation 5 is del u prime del t. So, we have to take a derivative with respect to t, right. So, that is going to be what it is going to be, that I alpha minus c, okay, this. So, you are taking the derivative with respect to time. So, I alpha minus c. Okay. So, minus I alpha c u hat, correct, u hat into the exponential term, which will be common in both the sides of this equation and will cancel out. Okay. So, this is the first term. What is the second term? Second term, that in that equation u into del u prime del x. So, that means del u prime del x, if we consider del u prime del x, that is going to be I alpha u hat u hat, and this is going to be u hat, capital U is going to be there, cosine phi is going to be there, right, plus what is there, w into del u prime del z. So, that is also you are going to get I alpha u prime, right, u hat, I alpha u hat w sin phi, okay, because del u prime del z is there. So, that is what it is. This plus another term is there in the left hand side, that is v prime del u del y. So, v prime means if we replace the value of v prime from this expression, then we get v hat into the exponential term, and that del capital U del y, that is nothing but or u prime, which is differentiation with respect to y, that is what we are saying. Okay. So, basically differentiation with respect to u, it is a total differentiation, keep it in mind, it is not del u del y. So, since we have considered it is a parallel flow, u is a function of y only. So, it will be total derivative. Okay. So, equals equals what, minus 1 by rho del p del x prime, okay, sorry, del p prime del x, okay, minus 1 by rho p prime del p del x. So, this is going to be I alpha cosine p hat which is a function of y only, cosine phi is going to be there, okay, into the exponential term which is common in both the sides and will get cancel out. So, this is the pressure term plus you get the viscous term which is nu into double derivative of u prime. Okay. So, double derivative of u prime if you consider, so that is going to be your if you consider single derivative of u prime, so that is I alpha u hat cosine phi. Okay. So, that is the single derivative, and double derivative of this term is going to be I square alpha square so double derivative of this is going to be I square alpha square, and this is your cosine square phi. Okay. So, this is your double derivative and plus what is there? Double derivative of u prime with respect to y. So, that means double derivative of u prime with respect to y. So, this is going to be simply this is going to be, so this is basically del u. So, that means it is going to be u hat double prime into your exponential term, okay, plus the last term is what, del 2 u prime del x 2, okay, del z 2 sorry. So, with respect to z. So, this is also going to be I alpha square u hat sine square phi into the exponential term. Okay. This is what you will get it. Okay. So, essentially if you see this term and this term will add, and this is going to be minus I square. So, I square is going to be there also. So, I square will be minus 1. So, that means u hat double prime minus alpha square u hat, that is what will be this term. That means, if we simplify this equation and write it, we can write this particular equation as so this particular equation can be written as let me take this term out. So, that means I, so or I alpha u hat I can take it out, I alpha u hat I can take common, I alpha u hat if I take common, then we are left with u cosine phi plus w sin phi minus c okay, plus we have another term, that is v hat u prime, v hat capital U prime, which is nothing but du dy. Okay. So, this equals in the right hand side, let us see. So, right hand side minus I alpha p hat cosine phi by rho plus what we get, nu into, as already mentioned, that u double prime, it is once again derivative with respect to y only, and u hat is only a function of y. So, this is total derivative, that means this is d2 u hat double prime dy2 minus alpha square u hat. Okay. let us call this equation to be 9. Okay. Let us call this equation to be 9. Similarly, from equation 6 and 7 we can write. Okay. So, from equation 6 and 7 we can write what? I alpha v hat u cosine phi plus w sin phi minus c equals to, this is going to be del p del y, del p prime del y. So, you are differentiating with respect to y only. So, this is p hat prime derivative with respect to y by rho into the exponential term, which is common in both the sides. So, it will cancel out, I am not writing that. Okay. So, this is plus nu into, here we can write v hat double prime minus alpha square v hat, and this equation let us call equation number 10. Okay. Similarly, if we use equation 7 with this normal root form, then we are going to get I alpha w hat u cosine phi plus w sin phi minus c, okay, plus this is going to be your v hat w prime, which is derivative with respect to, total derivative with respect to y, equals to your minus I alpha p hat, this is going to be your sin phi, because what is this term? This is your del p prime del z. Okay. So, p prime first you express in terms of normal mode, then have the derivative. If you do that, then this into this exponential term which is going to be there, but this is common in both the sides. So, we will cancel out, we are not writing it, plus this viscous term, that is your w hat double prime minus alpha square w hat, and let us call this equation to be 11. Okay. So, these are the 4 equations, equation 8, equation 9, 10 and 11 we got from equation 2, 5, 6 and 7 using the normal mode expression. So, we are still simplifying this equation. Okay. So, these are the 3 equations we have got, and if you see now one thing, if we multiply this equation 9 using cos phi, and if we multiply equation 11 with sin phi, and if we add them, let us see what you get. Okay. So, here, so there are 2 steps. First, we will consider this particular expression u naught as capital U cosine phi plus w sin phi. This expression we are designating as u naught. Okay. So, what is u naught? U naught is the velocity along the wave vector direction. Okay. Similarly, u naught hat, okay, let us consider this as u hat cosine phi plus v hat sin phi. What is this? This is the disturbance propagating along the wave vector direction. Okay. So, first we consider this. After this, what we do? We multiply this by cosine phi, multiply this equation 11 sin phi and add them together. Okay. So, if we do that, what do we get? So, let me write it here. Considering equation 9 into cosine phi plus equation 11 into sin phi we get what? So, I alpha u hat cosine phi, and this is your u naught minus c plus v hat u prime cosine phi equals to I alpha by rho p hat, right, plus nu and this is going to be u hat double prime cosine phi minus alpha square u hat cosine phi. Okay. So, sorry. So, plus the z component will come, that is your I alpha sin square phi by rho p hat plus nu your this is w hat double prime sin phi minus alpha square w hat sin phi, okay, and this side is going to be plus I alpha w hat sin phi u minus u naught minus c plus this is going to be v hat w prime sin phi. Okay. So, this plus this term, okay, equals to this. So, essentially, or we can write, you see, summation of these two we can write as what? So, summation of these two term can be written as, you see, that u minus c I alpha. So, basically I alpha will be common. So, I alpha u naught hat u minus c, okay, plus u c plus here v hat is common, and these two will be essentially your u naught prime, okay. That is what is going to be this particular term, okay. These two, summation of these two term is going to be v hat u naught prime equals to, you see, summation of these two term is essentially so this is 1. So, this is if you sum, this is going to be common and that is going to be 1. So, that is minus I alpha p hat by rho, okay. That is what we left with, plus these two term if we sum. So, this is going to be nu into your u naught hat double prime minus alpha square u naught hat, okay. So, this is what we get, and let us call, you know, this equation as equation 12, okay. So, this is what is our equation 12. Now, these three equation, to understand better, let me just write all these three equations together, okay. One is our continuity equation, another is this combined x and z momentum equation, and then y momentum equation, and from these three equations we will be able to, you know, conclude some interesting result, okay, and let us see what is that, okay. So, if we, you know, consider the continuity equation and this expression, then what will be, you know, our equation continuity equation what it was, I alpha cos phi I alpha u hat cosine phi plus I alpha u hat w hat sin phi plus the v term del v del y. So, that means that term is going to be your v hat prime, right, v hat prime. So, this is what our continuity equation. So, if you add these two terms, so that means our continuity equation if we write, that is going to be I alpha u naught hat plus v hat, this should be prime here, okay, because del v prime del y, that will come as the into that exponential term with all this, which will get cancelled out from both this side, and this is going to be 0. So, that is what is your continuity in continuity equation after using the normal mode form. Okay. So, this is what is our continuity equation. Then let me write the equation y momentum equation, that is your I alpha v hat u naught minus c. Okay. So, u naught minus c is equal to minus p hat by rho plus nu, this is v hat double prime minus alpha square v hat, this is the y momentum equation. And the last one which we have got here. So, let us just write that I alpha u naught, I should have written this equation just before. So, let me just put this equation little above. So, I alpha u naught hat plus v hat prime is equal to 0 continuity equation, then x momentum equation, which not x momentum equation combined equation along the wave vector direction is equal to I alpha u naught hat u minus c plus v hat u naught prime equals to minus I alpha p hat by rho plus nu u naught hat double prime minus alpha square u naught hat. Okay. So, this equation we have not derived yet. So, this is 12, we can call this equation 13, sorry. So, this equation 13, this equation 12 already we have named it, and this equation already named as 10, right. This equation we have already named as 10. Okay. So, these three equation, if we notice these three equation, it is just like two dimensional disturbance propagating along the wave vector direction. Okay. So, it is just like your two dimensional disturbance propagating. So, this is our x, this is our z, and this is our x, and we have considered wave is propagating in this direction, in this direction, and this is our phi, and the u naught is actually in this direction, and that u naught hat is also in this direction. So, that means this is the equivalent two dimensional equations or disturbance equation along the wave vector direction. So, now one interesting point here, you see we started with three dimensional disturbances and end up with this particular set of equation after manipulation, right. So, you see that actual three dimensional disturbances, if we consider, then u is the velocity along u is the velocity along the x direction. Okay. And what is the component of velocity in the wave vector direction? That is u cosine phi. Okay. U is the direction, this one is direction x, this one along the along the k direction, wave vector direction. Okay. This is along the wave vector direction. You see, if we consider if we consider the 3D disturbances which is propagating in this particular direction, velocity in that direction is smaller than the velocity in the x direction. Okay. That means, a 2D disturbance propagating in a 2-dimensional parallel flow will have the lower critical Reynolds number, because this is the Reynolds number if you define based on this velocity and based on this velocity using a same length scale, then this Reynolds number will be less. So, that means, the disturbance in that direction will be more stable as compared to disturbance propagating in the u direction. Okay. So, that is why that square theorem comes in picture. So, square theorem says that for a 2-dimensional parallel flow, the critical Reynolds number will be lower for a 2-dimensional disturbance propagating in the of the flow. Okay. So, for a 2-dimensional parallel flow or for a 2-dimensional basic parallel flow, the critical Reynolds number will be lower for a 2-dimensional disturbance propagating in the direction of the flow. Okay. So, that is what the square theorem. So, this says that if we consider 2-dimensional disturbances propagating in the direction of the flow velocity itself, whatever critical Reynolds number it will provide, that will be less than any other critical Reynolds number. Okay. So, that is why it is sufficient to consider these 3 equations to study the disturbance evolution. Okay. So, if we study the 2-dimensional disturbances, propagation of 2-dimensional disturbances in the direction of the mean flow or in the direction of the flow, that should be enough to obtain a minimum critical Reynolds number. That is what this theorem says. Okay. So, that means, now from these 3 equations what we can do, we can essentially remove this u naught and this capital U naught term and make these equations free from any u naught, considering that 2D flow we are considering, and the flow is and the disturbance is propagating in the direction of the flow. Okay. So, in that case these three equations can be written as same as those except the u naught. So, let me just write those equations for. So, for a two dimensional, so hence for a two dimensional parallel flow, okay, means we do not have w component, our velocity component is only u. Okay. So, that means earlier if you remember we considered that u as a function of y, v and w. Okay. So, here there is we are considering that we do not have these two component, our mean flow is just like this. Okay. It is a function of y only. So, for that particular case we will have the so hence for two dimensional parallel flow we get the following disturbance equations. Okay. And what are those? We can just remove this u naught, instead of that we can just write u hat plus v hat prime is equal to 0. So, this is let us say 14. Okay. This is what is our continuity, two dimensional continuity equation, and then our next equation, that is your I alpha, what is that? I alpha u hat u minus c plus v hat u prime minus I alpha p hat by rho plus nu u naught, instead of u naught only that u hat double prime minus alpha square u hat. Okay. Let us call this equation to be now 15, and that the last equation we there is no name, no need to rename, it will remain as it is. So, no, we can u naught we can anyway remove from that. So, we can rename this equation once again as So, let me just write this. So, here it was u naught. So, u naught can be removed to, and we can put u equals to minus p hat by rho plus nu v hat double prime minus alpha square, that is your v hat, and this equation 16. Okay. So, finally, we got the disturbance equation. Okay. And three disturbance equations, there are three variables u prime u hat, v hat and p hat. Okay. So, instead of these three variables and three equations, let us write a single equation removing u hat and p hat from these equations. So, okay. So, eliminating u hat and p hat from equation 14, 15 and 16, we get eliminating u hat and p hat from equation 14, 15 sorry 14, 15 and 16 we get. Okay. So, to eliminate the u hat and p hat, what we can do, the equation 15 we can take the derivative, we can take the derivative of equation 15. So, here there is a slight issue. So, here there should be a prime here, okay, p prime. So, there should be a p hat prime which is missed, okay, I am sorry. So, how we can eliminate, okay, p hat and u hat, what you can do, you see, you can take the derivative of equation 15 with respect to y, then replace the p hat from this equation 15 after taking the derivative in this equation, and replace the u hat with respect to v hat from this continuity equation or equation 14. Then you will be able to write an equation in terms of v hat only, and let us do that. Okay. So, first what we are going to do? We are going to take the derivative of equation 15. Okay. If we do that, so if we take the derivative of equation 15, then I alpha u hat prime u minus c plus I alpha u hat derivative of this term. So, that is nothing but your u prime, right, plus your v hat prime u prime plus v hat u double prime, okay, plus equals minus I alpha p hat prime by rho plus nu u hat triple prime minus alpha u hat, okay, prime. So, this is what we get, and from this equation we can remove this. So, now what we can consider? So, first instead of that we should have written, I am sorry, instead of this I should have written taking we get, okay. This is what we get after taking the derivative of equation 15. Okay. So, now from this equation we can get the value of minus p hat prime by rho. Okay. So, minus p hat prime by rho equals to, we can write this. Okay. So, this is bit involved. So, this is equals to then this minus that particular term. So, let me write I alpha u hat prime u minus c plus I alpha u hat u prime plus v hat prime u prime v hat u double prime minus nu u hat triple prime minus alpha, sorry, there should be alpha square here, alpha square u hat prime, sorry, u hat, yes, u hat prime. Okay. So, this is what we get from this equation. Now, this particular value, okay, we can replace in equation 16. Okay. So, hence get from equation 16, what do we get? You see, we write everything except we replace this particular term there. So, that means I alpha v hat u minus c equals to p hat prime. So, that value is basically is this. So, this is I alpha u hat prime u minus c plus I alpha u hat u prime plus v hat prime u hat prime plus v hat u double prime minus nu u hat triple prime minus alpha square u hat prime. Okay. So, you replace the value of this plus we have what? Nu into v hat double prime minus alpha square v hat. Okay. So, this is what we have. Okay. Hence, we get from equation 16 is this, because we have replaced the value of minus p hat prime by rho, and this is what we have got. Now, in this equation we have to replace that all u hat in terms of v hat from the equation 14. Okay. So, if we do that, let us see what we get. Okay. So, if we do that, there is a slight mistake, we have to correct that mistake here. So, see here, when we are writing that p hat prime by rho, so we have to divide, just forgotten to divide by this I alpha. So, there will be a 1 by I alpha in the left hand side. Okay. 1 by I alpha in the left hand side, then from equation 16, then we can write we are here this particular term into 1 by I alpha is going to be there. So, there where has been a slight mistake. Okay. So, now if you proceed, it should come. So, let us see, this I alpha will cancel out from these two. Okay. Or we can do one thing, this I alpha we can take it in the or we can multiply by that I alpha in both the sides, and let us see what we get. Okay. So, to get remove of this I alpha, we can multiply that I alpha in both the sides, and let us see. Okay. So, or I square alpha square v hat u minus c equals to, we can write I alpha u hat prime minus u minus c plus I alpha u hat u prime plus v hat prime u prime plus v hat u double prime. Okay. So, plus there are other terms as well, not plus, this is minus nu u hat triple prime minus alpha square u hat prime. Okay. So, this quantity plus we have multiplied by I alpha. So, I alpha nu should be here as well, and this is going to be v hat double prime minus alpha square v hat prime. Okay. Now, we have to use the continuity equation to remove the your u. Okay. So, if you do that, okay, so here we can write this term rather as minus, sorry, this should be I square. So, I alpha we are multiplying in both the sides. So, I square alpha square. So, that should be minus alpha square v hat u minus c equals to I alpha u hat prime. I alpha u hat prime is equal to is going to be your minus v hat double prime u minus c. This is coming from continuity equation. Okay. So, then I hat u prime is equal to I alpha, okay, u hat is equal to I hat u alpha is equal to minus v hat. I alpha u hat is equal to minus v hat prime, okay, minus v hat prime, okay, and u prime, okay, plus you see that v hat prime u hat prime, they will cancel out here v hat u double prime, okay, minus this nu. So, nu into u triple prime. So, from continuity equation this is going to be minus v hat divided by I alpha, okay, minus alpha square u hat prime. U hat prime is equal to v hat double prime divided by minus. So, this is positive I alpha. Okay. So, this is what is going to be the last term. Now, let us see what we get after simplification. So, these two term we can take it in the left hand side, and you see this term and this term will cancel out. This term also we take it in the right hand side. One more term I think is left. This term we have to, so we have replaced the value of this term, okay, which is this. So, we have to write this plus I alpha nu v hat double prime minus alpha square v hat prime. Okay. So, let us see, it is a bit involved, but it is doable. So, anyway, this term if we take in this side, then we can write u minus c v hat double prime minus alpha square v hat, okay, minus this term v hat u double prime. We are done with the left hand side. Right hand side we are there. So, right hand side nu I by alpha, okay. If you do that, then you see what we can do. I can multiply by alpha in both these sides. So, this is basically I square minus 1 minus will cancel. So, I will be there, here also I will be there. So, this is minus will be there. So, that means what is going to happen here, v double prime, sorry, v quadruple, right. So, this and this alpha has come out. So, this one I is going to be there, that I has also come out, and here alpha has come out, one I is there, I has come out, and this has become minus. So, alpha square v hat double prime. Then here we have taken out this, okay. This has come, this has come. So, alpha, so that means that alpha we have taken. So, alpha square. So, that means this is going to be minus we have taken. So, that is going to be minus alpha square v hat prime So, here no prime is there. Okay. So, there is a mistake here, no prime will be here. Okay. Sorry. So, no prime is going to be there. Okay. So, the last term, so that is v double prime alpha square v hat, okay, no prime. So, this one and what is this? So, writing this term. So, we are done with this term, that is this term is done. Now, this term is left. So, alpha square is going to be there. So, that is going to be nothing but your so this is minus has gone out. So, that means that is positive and it is going to be alpha to the power 4 v hat. Okay. So, I think now it is okay. If we okay, I think this is fine. Okay. So, now if we see this particular equation, or you see what is the simplified form of this equation, v hat double prime alpha square v hat minus v hat u double prime and minus nu I by alpha v hat minus 2 alpha square v hat double prime plus alpha to the power 4 v hat. So, finally, this is what is our equation. Okay. This is what our disturbance equation. Okay. This is very, very important. Okay. So, this is what is our disturbance equation and it is fourth order ordinary differential equation of variable coefficient. Okay. Why variable coefficient? Because u is there, u is a function of y. So, y hat or v hat is also a function of y. So, it is a varying or variable coefficient. This is a variable coefficient ODE. Okay. So, there is no straightforward solution of this equation. So, we have to rely on some numerical techniques to solve this equation. Anyway, before we proceed with this, so this is the equation and we have to find out the eigenvalue of this equation. Why? I will come to that. Just let me quickly tell you this particular equation is known as Orr-Sommerfeld equation, because this particular equation was derived independently both by Orr and Sommerfeld. Okay. So, this equation is known as Orr Sommerfeld equation, okay, who derived this equation independently in 1907 and 1908. Okay. So, that is why this equation bears their name. Okay. So, this is a fourth order ordinary differential equation. Okay. Fourth order ordinary differential equations. What are the boundary conditions? Boundary conditions. Okay. So, the boundary condition, it is a disturbance equation and we want the disturbance to be 0 in the far stream as well as on the wall. So, that is the main condition. Okay. So, disturbance, that means for duct flows, for duct flows means flow through a channel, for example, both side wall. Okay. Let us say the wall is at plus minus h. So, that means disturbance, this equation of v hat. So, that v hat at plus minus h should be 0. Okay. Similarly, if V hat at both wall is 0, then your the streamwise disturbance U hat, that all should be 0. If U hat is 0, from continuity equation what we know? We know that I alpha U hat plus V hat prime is equal to 0. So, that means if this is 0, then this condition says that not only this, actually V hat prime at plus minus h should be is equal to 0. So, fourth order equation you have 4 boundary conditions, okay. And this equation is a homogeneous equation. So, homogeneous equation with homogeneous boundary condition we get, or this equation is basically can be solved as eigenvalue problems, okay. So, that is the point. So, for boundary layer flows, your boundary conditions V hat at y is equal to 0 is equal to 0, at V hat prime at y is equal to 0 is equal to 0, and V hat at y is equal to infinity is equal to 0, V hat at infinity prime, okay, is equal to 0. So, this is for boundary layer. Similarly, for free shear flows, the boundary conditions are V hat at plus minus infinity equals to V hat prime at plus minus infinity is equal to 0. Okay. So, these are the 3 boundary conditions for 3 different flows for this equation. Okay. So, as I have mentioned, this equation is a homogeneous ordinary differential equation of variable coefficient with homogeneous boundary conditions, means it leads to eigenvalue problem. Okay. That means, for a given value of alpha u, okay, you can find out the value of, you can find out the value of c, okay, or for a given value of c u, you can find out the value of alpha which will satisfy this equation for the given conditions. Okay. So, that is what you have to keep it in mind. Okay. So, only a particular set will satisfy this equation, only a particular set for a particular value of Reynolds number, this equation is going to be satisfied. Okay. So, anyway, I know that today's class is bit boring because it is lot of derivations, but you do this, you practice this so that your fear will go out. Okay. If you practice this, so do this, so this equation is Orr-Schmor field equation, which is the main equation which will tell us whether small disturbance, if you add a small disturbance to a laminar flow, whether that flow is going to be stable or unstable. Based on this equation, we can have some idea. Okay. So, that is the point. Okay. So, you please look at this derivation. We will again meet in the next class to talk about more about this equation. Okay. Thank you.